Hello, everyone. My name is Chang Yang, and I'm a PhD student in the Hong Kong Polytechnic University. The paper I will be presenting today is titled DeepEar Sound Localization with Binaural Microphones. For sound localization, most methods are based on microphone array. At least we need 3 microphones. Therefore, if we only have 2 microphones, this method cannot work anymore. For example, if we measure the time difference of arrival between these 2 microphones, then any points as this hyperbola may be the potential locations of sound source because they have same TDOA. But we have no extra microphone pairs to plot another hyperbola to locate this position. So there is an ambiguity problem in 2 microphone localization cases. However, in some real-world scenarios, localization with 2 microphones is sometimes quite necessary. For example, there are many humanoid service robots. When a user talks to a robot, the robot should figure out the voice direction with their ears and turn their head to the user and provide customized service. People with hearing difficulties often wearing the hearing aids. If this device can detect the sound location, then the microphone in the ear can amplify the sound from this specific direction. Then it will substantially improve the sound quality when the user talking to the others. So here we may ask a question. In this case, how to locate the sound source with only 2 microphones? We observe that we, as humans, have the natural ability to locate multiple sounds simultaneously. For example, we can easily hear the people talking around us. But we also have only 2 ears, just like 2 microphones. Why can we locate multiple people talking at the same time? Actually, it is because that humans have ears and a brain. As shown in the red figure, when the sound travels to the ears, it will be scattered, reflected, and diffracted by the peanut structure. So this special reflection pattern will slightly distort the sound. Then the reflection pattern can be learned by our brain to locate the sound source. So next, I will briefly introduce the mechanism behind and then propose our design. So let's have a look at the human auditory system. Don't worry about these complex biological terms. I will give an intuitive understanding for them. First, the sound will travel to the ear, and the ear will bring unique reflection patterns to the sound from different directions. Next, in cochlea, we can see here like a snail, it will transform the sound into the electrical stimulus signal. Then, along the nerve path, many brainstem nuclei will encode the signal to perception. After that, the auditory cortex in human brain will interpret this perception as the cognition of sound direction. So, inspired by this mechanism, we design a bionic framework to mimic the functions of human auditory system. So we first use binaural microphones to record the sound and use some filters to imitate the function of a cochlea. After that, some deep learning models are used for signal encoding and the location inference. So in the following, I will introduce them one by one. Unlike the general microphones, we use binaural microphones attached with 2 ears. I guess many of you have seen this microphone before. As we mentioned, the ear will distort the sound and cause the unique reflection patterns. We note that this sound from different directions will have different reflections in the ear. So this spatial pattern actually is direction dependent. Thus, a human brain can learn this pattern to perform localization. To validate this argument, we use a loudspeaker to transmit excitation signals and measure the frequency response in the ear. As shown in the left figure, we can see that they have a significant difference with and without ears, no matter for left ear or right ear. Also, we put the loudspeaker at different locations. We can see the frequency response at the front and the back locations also have quite different patterns. After the sound is distorted by the ear canal will guide the sounds to hit this eardrum. And then the eardrum will push and pull the small bones to press the cochlea. In this way, the sound will be transformed into the electrical nerve signal. We can see here, the cochlea has a spiral shape, just like a snail, and its different parts would vibrate in response to different frequencies. Then the time domain signal will be further decomposed to the frequency domain. So to mimic this special function of cochlea, we use a gamma tone filter bank to transform the sounds into frequency domain. After transformation, the electrical signal will pass through the nerves and be compressed and encoded by a series of brainstem nuclei. We know that the number of cells in hearing nerve is very huge. So this encoding process is used to extract the most useful information to prevent overloading the brain in a very short of time. So this function actually like an encoder. We know that an encoder can compress or encode the data without much information loss. So we use a variational autoencoder to encode the data into high-level representations like the brainstem nuclei. So this signal passed through gamma tone filter bank is a 2D matrix with the temporal information. Thus, we use GRU as the encode layers. We can see here the original input and the reconstructed output of the autoencoder are very similar, which means it can extract most representative features from the input automatically. The final step is location inference. Conventional methods usually use single label classification, which means the model only outputs one result and locates only one sound source. So they can't support the multiple sound scenarios. For this reason, we formulate the multiple sounds localization as a multi-label classification problem. Specifically, we divide the 2D space into several small sectors, for example, 4. Each node represents each sector. Then we train each output nodes independently. Thus, our model can output multiple results simultaneously to support the co-active sound source. We can also increase the number of subsectors to adjust the spatial resolution as we need. This multi-label classification network is used for sound detection, which means to detect if there is an active sound source in this sector area. In addition, we design a multitask learning structure jointly minimize the loss of sound detection, direction prediction, and distance estimation. Here is an overview of a DeepEar structure. We can see that the sound of left and right ears pass through a gamma tone filter bank. Then a variational autoencoder is used to encode the data into high-level features. we also introduced the cross correlation between two channels as a part of features, because it contains the time difference between the 2 ears, which is very important to sound localization. Moreover, to obtain the power difference between 2 ears, we perform a subtraction between two feature vectors, then concatenate them all together as the final feature vector. We use some simple dense layers to construct the inference network. So in this paper, we set the number of special sectors as 8. For each sector, accordingly, we have a sector subnet. In each sector subnet, it includes 3 small nets to detect the sound source, predict the angle of arrival, and estimate the sound distance. These 8 subsectors share a similar structure. Now let's move to evaluation parts. We use the 2 Berlin spatial sound dataset. It contains 3 rooms, 1 anechoic chamber, and 2 reverberant rooms, including a lecture room and meeting room. Considering that there are not too many coactive sound sources in our real life, we set the maximum number of sound sources as 3. The sound sources are sampled uniformly in random locations. Then we select 18% of anechoic data for model training. Then this model is tested on the remaining anechoic data, the meeting room data, and the lecture room data. We choose a baseline named the wavelog, and it is raw waveform-based end-to-end CNN approach. In anechoic environments, the average sound detection accuracy is 93%. If only focused on positive class, the Hamming score is 83%. The angle of arrival estimation error is about 7 degrees, and the distance classification accuracy is 83%. We can see that the performance in one source scenario is the highest, and it decreases with the number of sources increase. In addition, we can see the DeepEar always outperform the wavelog, no matter for which cases. We also test the model on the data in meeting room. Unfortunately, the sound detection accuracy drops to 65%, and the angle of arrival error increased to 16 degrees. It is in our expectation because we train the model on the anechoic data, but tested on the reverberant data, which means they are 2 totally different environments. So to enable DeepEar to adapt to new environments, we explore the transfer learning strategy. Specifically, we have already trained this global model with massive anechoic data, and thus we can keep the previous layers frozen, then fine-tune the model with the data in a new environment. So we can see, as the figure shows, the dark bar refers to the performance before transfer learning, and the light bar denotes the performance after transfer learning. We can see after applying the transfer learning, the sound detection accuracy again increased to 92%, and it is almost the same as before. And the LA estimation error also decreased by half. Similarly, direct testing DeepEar on lecture room data also has a performance decrease, and the transfer learning can effectively recover the system performance. We also evaluate the performance of transfer learning with different size of data. We can see that in both meeting room and the lecture room, only 2% of data are enough to boost the DeepEar performance. It is because that we already use massive anechoic data to train a global model. Thus, the DeepEar can adjust the feature space with only a small number of new data and quickly adapt to the new environment. We also conduct a real-world study to evaluate the importance of ears for sound localization. As the left figure shows, we use a loudspeaker as a sound source placed at 8 different locations around the binaural microphone. Then we implement a simple one-layer LSTM network to perform the sound localization task. We can see the confusion matrix with and without the ears. When we detach the ears, the localization accuracy is 58%. Obviously, the model can hardly identify the degrees in the left side or right side. Also, it confuses the direction at the front side and back side. So it suffers from the symmetric sound confusions, as we mentioned in the beginning of the talk. By contrast, the overall classification accuracy increased to 92% after molting the ears, which means the ears indeed help a lot to improve the sound accuracy. So here I want to give a takeaway message of this talk. Ears indeed play a significant role in sound localization and disambiguation. To conclude, we propose a DeepEar, the first sound localization system for binaural microphones without a prior knowledge of the sound's number. DeepEar is a bionic machine hearing framework inspired by a human auditory system. Of course, we can replace the encoder or inference network with other powerful backbones like transformer. Finally, with transfer learning strategy, DeepEar can quickly adapt to new environments with a small number of extra training data. Okay, that's all for my presentation, and I welcome any questions. Thank you.